Good evening. We're going to consider in this video how to expand powers of x plus y. Now, in case you're tempted to just try to make that x to the n plus y to the n, consider a simple example, x plus y squared, which of course is x plus y to the x plus y. And because we multiply with distributing or FOIL, sometimes it's called, you end up with x squared plus 2xy plus y squared, which is definitely not x squared plus y squared. So, we're on the alert that we're going to need some kind of pattern or formula or theorem to tackle this for us, and that theorem is going to be the Binomial Theorem. And to develop this theorem, I'm going to start by taking a look at the smallest possible powers. So if we have x plus y to the 0, anything to the 0, of course, is equal to simply 1. And so I can write that as 1. If I have x plus y to the first, then anything to the first power is itself, so that I get x plus y. And we already saw that x plus y squared is equal to x squared plus 2xy plus y squared. You may have noticed that I'm writing these results on the right side over here in a triangle format, but there's a reason for that. Keep watching what happens in the triangle. Now things get interesting. How would I write x plus y cubed? Well, I could write that as x plus y times x plus y times x plus y. Let me do that temporarily off to the side over here. But the thing is that I already know what x plus y times x plus y is because I computed that in the previous row. So I'm going to write this then as x plus y times the result from the previous row, which was x squared plus 2xy plus y squared. Well, how in the world do I evaluate this guy? I do it by distributing. I'm going to distribute x to each term, and then I'll come back and distribute y to each term, just like so. And when I do this, rather than write the whole mess out, I want you to see what we get. We end up with x times each one of these terms, plus y times each one of these terms. And again, instead of multiplying the whole thing out right here, what I'd like to do is to go over to my arrangement and see how that would work. What I'm going to do is to take each term and I'm going to multiply it by x. And then I'm going to come back and I'm going to multiply each term by y. And you notice that when I do that, that some of these terms are going to overlap each other. This first term is just going to be x squared times x, no problem. This next term is going to be x squared y plus x squared y here plus 2x squared y here. And when I add those, I get 3x squared y. And for these two terms here, I'm going to get 2xy squared plus xy squared, or 3xy squared. And for my final term, I'm going to get y times y squared, which is 1. Well, that was some work, but I think it was a lot less work than multiplying all of these guys here and then trying to add them together. It was also a lot less error prone. So let me erase some of the scrap work. In fact, rather than erase it, what I'm going to do is just collect it, group it, shrink it down, and get it out of the way. And now we want to consider how the next row would go, which is x plus y to the 4th. And using that same idea of multiplying each term by x and multiplying each term by y and adding those together, then I can see that my first term is going to be x to the 4th plus. And here we're going to take and multiply this term by x giving us 3x to the 3x cubed y. And we're going to multiply this term by y, giving us x cubed y. And 3x cubed y plus x cubed y is 4x cubed y. And I think you can see what's going to happen. In my next term, I'm going to get x squared y squared. How many of them? 3 here and 3 here, for a total of 6. And in my next term, I'm going to get xy to the third, 3 here and 1 here, for a total of 4. And in my last term, I get a single y to the fourth. Well, this gives a nice pattern, but how would I describe that pattern? I would describe that pattern by saying that first of all, that if I have x plus y to the n, then I am going to get n plus 1 total terms. You can count here and see x plus y to the fourth gives me 1, 2, 3, 4, 5 total terms. 5 total terms. And those terms are going to be in decreasing powers of x. My powers of x are going to decrease from 4 to 3 to 2 to 1 to 0. And in increasing powers of y, from 0 to 1 to 2 to 3 to 4. So we have decreasing powers of x, n all the way down to 0. And we have increasing powers of y, from 0 all the way up to n. Okay, now what about the coefficients? Remember, the coefficients are the numbers that are here, and the invisible coefficient is 1, of course. Let's give a symbol to our coefficients, and then we'll try to describe the pattern that's going on with them. The symbol that we're going to give is going to come about from the value for n. So in our 0th row here, n is equal to 0, n is equal to 1 in this row, 2, 3, and 4 in this row. N is the same as the power that I am raising x plus y to. And now we're going to come over and count terms starting at 0. And we're going to give the symbol r to the value of our term. This is going to be the 0th term. R is equal to 1, 2, 3, and 4. Notice that r has the exact same value as the power of y in this term. So in this term, r is 2, and y, the power of y, is also 2. And we're going to use the symbol in choose r, is how this is pronounced, to represent the coefficient in the nth row and the rth item over. Both of those starting at 0. So, for example, I can read immediately the coefficients are in choose r. I can read immediately that if I want 4 choose 2, then I can determine that just by going down to n equals 4, that's this row, and counting over 0, 1, 2, and n choose 2, 4 choose 2, excuse me, would be 6. Likewise, if I wanted 3 choose 1, then I would go down to the row n equals 3, and I would go over 0, 1, and read off the coefficient there, which is equal to 3. So, we can write a tentative result here. We can say that x plus y to the n is going to consist of terms that start with x to the n, y to the 0, and then go in increasing powers of y and decreasing powers of x until we get all the way down to y to the n and x to the 0. And we can say that the coefficients here are going to be in choose 0, in choose 1, choose 2, n choose n minus 1, and n choose n. Well, that's all fine. I mean, we have our theorem, and this is the binomial theorem. But the real big question we have is, how do we compute these choose numbers? What I'd like to do now is to show you a couple of ways to compute the choose numbers, and then we'll do some examples so that you can see that this really does make sense and work. Let's come back to the triangle that we have right here. And what I'd like to do is to look at just the coefficients, so that if I write just the coefficients, starting at 1, that's x plus y to the 0, and then I can write 1, 1 for 1 times x plus 1 times y, and that's for n equals 1. And then I can write 1, 2, 1 for my coefficients in x for x plus y squared. Then a pattern begins to emerge, and that is that each element in the nth row is equal to the sum of the two elements directly above it. So if I take and add 1 plus 2, I get 3 here. And if I want to generate the next row, then I can start at 1 on the outside here, and I can just go through and add. 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4, and 1 on the outside. So this gives me at least a method for computing n choose r for small values of n and r. Let's try the next row. In fact, at this point, if you think you have the pattern, you can go ahead and pause the video and try to generate the next row and tell me what you get. Welcome back. Hopefully your row looks just like this. Excuse me, not that. There we go. That row looks just like that. So we could now use this triangle, which is called Pascal's triangle. Blaise Pascal was the first person to discover it, and he was actually using these choose numbers as a way of gambling. He was interested in, or at least doing the mathematics of gambling. So if we wanted to compute, for example, 5 choose 2, then we would count n equals 0, 1, 2, 3, 4, and now 5. And then we would count r as 0, 1, 2, and that would tell us that 5 choose 2 is 10. There are a lot of different really interesting properties of the choose numbers. But I want to show you a couple that are pretty obvious from the triangle. And the first thing that I want to show you is that n choose 0 is always 1. N choose 0 is going to be the outermost numbers here, and because the outermost number is generated just by carrying down the 1 from here, n choose 0 is always 1. And likewise, n choose n is always 1 as well. The second thing that I want you to observe is that the second row along this line, row number 1, is always equal to n. So n choose 1 is always equal to n. And that's pretty clear because what we're doing as we go down in rows is we're adding 1 to the previous one, which means that this row is going to go up by 1 every time. I can't help myself. I get started on a row, and I just want to complete it. You know? Then the last thing that I want to observe is what we call the property of symmetry. And that is that the elements going in from the left are the same as the elements going in from the right. And we can express that like this, that in choose r is going to be the same as in choose n minus r. These are the properties that I want you to observe, and tomorrow in class we're going to need these two properties in particular. Now let me show you how this works for small values of n and r, and then I'm going to give you a formula that is going to work for large values of n and r if you happen to need them. So here's an example. Suppose I need to simplify x minus 2 to the third power. Using the binomial theorem, I can write that with decreasing powers of x to the 1, of course, is just x, and x to the 0 is going to be 1, which is invisible, and increasing powers of y, starting at 0 and working our way up to 3. And now, excuse me, I'm so used to doing the y here. The y value that we have is actually negative 2, so I need to use the appropriate y. And I apologize for being done already there. So let me say that all again. We're going to start with powers of x at 3 and going all the way down to 0. We're going to start with powers of negative 2 going all the way up to 3. And then our coefficients are going to be 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. And I can go back to my triangle to row number 3, and I can read the choose numbers directly off that triangle. So reading those values, we get 1 for the first one, we get 3 for the next one, we get 3 for the next one, and we get 1 for the last one. And that gives us x cubed minus 6x squared, that's negative 2 times 3, plus 4 times 3 is 12x, and then this would be minus 8. Now, if it strikes you that this is a fair amount of work, yeah, it kind of is, although it gets faster the more you do it. But I want to ask you this, what's the alternative? Well, the only other alternative would be to write out x minus 2 3 times, and then multiply that out. And you might think that for a cube, that's not too bad, but you can imagine that for a 5th power or a 6th power, it might get really formidable. So that we get better at this, I'd like to try one more, and then I'll close with the formula for large n and r. Let's do this. Let's simplify x plus 4 to the 4th power. Okay? So I'd like for you to do this. First of all, write out your decreasing powers of x times your increasing powers of 4. Go ahead and do that. Welcome back. What you should have is your skeleton. X to the 4th times 4 to the 0, plus x to the 3rd times 4 to the 1st, plus x to the 2nd times 4 to the 2nd, plus x to the 1st times 4 to the 3rd, plus x to the 0, which is invisible, times 4 to the 4th. And then our coefficients are going to come straight off the row for n equals 4, which is this row right here. They are 1, 4, 6, 4, 1. 1, 4, 6, 4, and 1. Now does it seem a little easier? And so I get x to the 4th plus 4 times 4 is 16, x to the 3rd, plus 6 times 16 is 96, would you believe it? X squared. Plus 4 times 64 is 256, x, plus 4 to the 4th is 256. And if you're not sure about the arithmetic there, you can check it on calculator. So you can see that once you get proficient with using the binomial theorem, this is much, much faster than multiplying out 4 powers of x plus 4. Now, where does all this take us? Tomorrow it's going to take us into a formula that will compute the derivative of x to the n. But I want to close, as I said, this evening with a formula that will give us a general expression for n choose r, and it's especially appropriate for large numbers. I'm not going to prove the formula at this time. However, in Calc 2, we do actually prove this formula, and it's a delightful proof. Here it is. N choose r is computed as n factorial divided by r factorial, also divided by n minus r factorial. Remember that n factorial means n times n minus 1 times n minus 2 times all the way down to 2 times 1, just like that. And we have a special value we define the number 0 factorial to be 1, which it seems a little strange, but it will make sense when you take Calc 2. So to apply this formula to what we have already seen here, let's take a couple of these choose numbers that we've already computed off of our Pascal's triangle and see how the formula works. I claim from the triangle that 5 choose 2 is equal to 10. Let's check that with our formula. That should be equal to 5 factorial divided by 2 factorial divided by 5 minus 2 is 3 factorial. Notice that the 2 and the 3 here add together to give you 5. Like that, just as a way of checking that you're plugging in the right numbers. Now let's multiply all that out. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 3 factorial is 3 times 2 times 1. One of the reasons that this is really nice is that the tail end here always cancels out some of the factors. So what you end up with in this case is 5 times 4 is 20, divided by 2 times 1 is 2, and we get 10 as advertised from the triangle. And as I mentioned, this is really nice for large numbers because if I need to compute something like, oh, I don't know, how about 12 choose 3, something like that. Then I can write that immediately as 12 factorial over 3 factorial times 17 factorial. Excuse me, 17, where did that come from? 9 factorial. There it is. And remember that the tail here always cancels out, so that what I end up with is 12 times 11 times 10, and all the other factors cancel, divided by 3 factorial, which is 3 times 2 times 1. And now 12 divided by 3 times 2 is just 2, and so I get 2 times 11 is 22 times 10 is 220. And that computation was a lot faster than computing 12 layers or 12 rows of your Pascal's triangle. Well, I hope this has been interesting to you. It's not obvious yet how we're